we'll do two examples. The first is a simple, nonlinear transform, the second order polynomial transform, to show you how we can compute the dot products in the feature space without ever going there. And then the miracle of the day. How can we compute dot products for a transform that takes us to an infinite dimensional space? That allows us to do learning in infinite dimensions. Wow! That is superpower. Okay, so example. So the simple example first. Okay, second order polynomial transform. So we have x, it's intensity symmetry, let's say, so two-dimensional x, x1, x2, okay, and that goes to z, which is x1, x2, x1 squared, x1, x2, x2 squared, and I'm going to put a square root of 2 here. So it's the standard polynomial transform. It doesn't affect the polynomial transform, it just makes the algebra more convenient. Okay. Now, if I'm going to run my optimal hyperplane algorithm in my z-space to do the maximum margin linear separator, okay, then I need to be able to compute the dot products in my z-space. So I need to be able to compute z dot z prime for any two vectors in my z-space, z and z prime. Well, what are these? This is just phi of x transpose phi of x prime. Okay, so I need to be able to compute phi of x prime. So let's look at a second data point, x prime, which is x1 prime, x2 prime. Okay, so this transforms to z prime, which is x1 prime, x2 prime, x1 prime squared, square root of 2 x1 prime, x2 prime, and then x2 prime squared. Okay. So if I take the dot product of these two, z dot z prime is just exactly equal to x1, x1 prime, so x1, x1 prime, plus x2, x2 prime, x2, x2 prime, plus x1 squared, x1 prime squared, plus x1 squared, x1 prime squared. Okay, plus x2 squared, x2 prime squared, x2 squared, x2 prime squared. Okay, plus, now this is where the convenience of the root 2, plus square root of 2 times square root of 2 is just 2, so we get plus 2 x1, x2, x1 prime, x2 prime, x1, x2, x1 prime, x2 prime. Okay. Now, I leave it to you to do the algebra to show that this is exactly equal to, okay, is exactly equal to x1 x1 prime plus x2 x2 prime plus 1/2 squared minus 1/4. Okay, so let's see. So x1 x1 prime squared gives me x1 squared, x1 prime squared. Okay, x2 x2 prime squared gives me x2 squared, x2 prime squared. Okay, 1/2 squared gives me 1/4 minus 1/4, so that'll disappear. Okay, now let's look at the cross terms. There's the cross term that involves x1 x1 prime times 1/2 times 2, so that's just x1 x1 prime. Boom. There's a cross term that involves x2 x2 prime times 1/2 times 2, so that's just x2 x2 prime. Okay. And there's one more cross term, which is this guy times 2, which is exactly that guy. Okay. And so this is equal to x dotted into x prime, so that's that term, plus 1/2 squared minus 1/4. Okay. Wow. Okay. So this dot product in the z space is equal to this function in my x space. Okay. So if I wanted to compute dot products in my z space, I can take my x values, my x vectors, and just compute this function. This is exactly what my kernel is going to be. Kernel of x and x prime. In other words, I have managed to represent the dot product in my z space using a function in my x space. And all I need to make this algorithm run are dot products in my z space, and I replace them by functions, by kernels, by the kernel function of my data points in my x space. So I don't physically need the z. Okay. Now, just to illustrate, a side note, you could do this comparable transform to the qth order polynomial, and you'll get a lot of terms here. Okay. And it turns out that you can construct the transform so that the corresponding kernel is exactly x dot x prime plus 1/2 to the power q, minus some constant c. Okay. And so this kernel corresponds to taking the inner product, the dot product of transformed vectors with respect to the qth order polynomial transform. Now, if you wanted to, you could actually take the dot product, and it's going to be a humongous dot product. Okay. The complexity is rising quite rapidly with q. Or you could stay in your X space, compute this kernel, which is equivalent to the dot product. And let's look at the runtime here. You take the dot product, that's just order of the dimensionality of my original space, which is 2. Does not depend on the number of dimensions in my qth order space. So this is a quick operation, order of 2. Now you raise this number to the power q. That's easy. And then you subtract a constant. This is essentially instant. Okay. Huge computational savings. Okay. While going into that space and performing the dot product physically is tedious, computationally intense. Okay. So this example illustrates two concepts. Well, the first, we can run this entire algorithm in this z space without visiting the z space by using this kernel, which miraculously computes this dot product. And all I need is to be able to miraculously compute dot products to run that algorithm. The second thing it illustrates, the second concept is, wow, look at the speed gain. This is essentially instant. This is going to be a rapidly costly, inner product computation if I actually transform there, depending on the order of the polynomial. This is called the qth order polynomial kernel. Qth order polynomial kernel. So let me erase and show you this exact process, but now transforming me to an infinite dimensional space. Okay? And then the end of the idea is, okay, look, in this particular example, I was able to sort of mathematically analyze the transform and construct the kernel. Okay. And in the next example, to infinite dimensional spaces, we're going to be able to mathematically analyze the transform and construct the kernel. Okay. But what if you cannot do that? Then you have no choice. You have to transform into that space. Okay. And that's where we play the game of we get to choose the space we want to transform to. So you choose a space to transform to for which there exists a kernel. Okay. And then we reverse the game. We say, you know what? I don't even want to choose the space to transform to. Can I just pick the kernel and assume that there's some space that corresponds to that? And by and large, yes. Okay. It turns out that if this kernel satisfies the basic properties that an inner product should satisfy, that means that it is symmetric and positive definite, then any kernel that's symmetric and positive definite corresponds to some z space. And now we don't even need to know the space we're going into. Okay. So that's the immense power of the kernel. But, having said that, let me come back and do this example to infinite dimensional spaces, and that gives us the ability to learn in infinite dimensional spaces. Wow! Okay. So, transforming to infinite dimensions. Learning in infinite dimensions. Where have you seen that before? Have you ever seen that? The ability to learn in infinite dimensions?